different light source. Okay. Now they have a big market. Okay. I believe now people just change with some other light source with LED very cheap, sell energy. So I think your critical understanding or light emitting diode is quite important. Okay. I think as an RTP student, I think your understanding on safety should be upgraded. Okay. This is very important. So let me give you an example how to understand LED at a different level. Okay. If you're undergraduate student, it's a UG student. Okay. Okay, UG student, I think your understanding of LED is something like this. Oh, you know it's a PN junction. Okay, no PN junction. Okay. Oh, it has a bias. You have bias, positive, and negative. So there's a hole, there's an electron that move, they combine, emit light. Okay, emit light. This is undergraduate student level. Okay, you know the light incoherence? Okay. I mean the phase direction will be randomly. Okay. So this is a basic undergraduate level. Okay, you know it's just electron hole pair recombine with each other, just generating light. Light is incoherent. Okay. But why they can recombine? Because it's at a bias. Okay. This is UG student level. I think you can know this. I think it's good enough. But if you're a master, I think the situation is quite different. Okay, your master should understand what you call it's a Venn diagram in the semiconductor physics. Okay, instead they have a P type, or P type there is it's a valence band, it's a conduction band. Oh, this is P type, so it's something. Oh, this has a Fermi level. E, F. Okay, this is for P type material. Down. For N-type material, the cut is a conduction band, valence band. Okay, this is N-type. This is P-type. This is the Fermi level. For B, N-type. Oh, this is before. When you touch them, okay, see what happened. Because they have lower Fermi level, so they will. I just draw this. Okay. It's a lower Fermi level, so they will go up, but somewhere will go down. Okay, this I just show this go down. Let's go down. This silicon, I just see the oxygen. Okay. So they have same Fermi level, finally. This is the PN junction. This is PN junction. Okay. This is the same Fermi level. Okay. This is same Fermi level. And here is a VDI. We call this building potential. Okay, this is okay, thermal equilibrium case. This thermal equilibrium case. This thermal equilibrium case. However, added bias. Okay, now it's bias, forward bias here. Okay, well, added forward bias is non-equilibrium state. It's non-equilibrium state. Non-equilibrium. See what happened? This is quite interesting. At first, this will become narrow. Here, it's not VBI, but VBI minus V. Okay, we apply. Okay, this is the first chain for the band structure. Another, the Fermi level cannot align, right? Okay, so for the P side, it's something. The P side is something like this. Something like this. Okay, go down. For N side, it's something like that. This for P side initially is align the valence band. Okay, they go down is a depletion region. Okay, the depletion region like something like this. This P side. Okay, this E F P. So for N side, it's something like this. They go down here. And go down here. This is just E F N. Just different color would be better. Change this color. Okay, something like this. Okay, this is E and N. This line is E F P. The Fermi level are now aligned, and the distance between two Fermi levels is around we apply. Okay. This is something, if you're a master student, you should understand this. Okay. Initially, PN junction has a same Fermi level, a thermal equilibrium. You add a bias, so you have non-equilibrium state. They have two different Fermi levels, okay, at P side and N side, okay, but the distance just apply the voltage. This is a master student. Understand. For PhD students, they go enough. Not enough to understand this level. Because until now, no equation, no government equation. What's the LED? What's the AD? Okay. So this is a mass student. I know this mass student level. 3. If you're RPG student, what level should be achieved? Understand LED. I think the important thing is the Gaussian equation. What's the Gaussian equation for LED? The interesting Gaussian equation is J, the Shockley diode equation. J0 E V or KVT minus 1. Okay? If no bias, no current, okay? If add a bias, the J is exponential increase. It's Boltzmann statistics. Okay? This is very similar to solar cell. The solar cell can put a photocurrent, but no, they have no photocurrent. Okay? So I draw this line, it's V, it's J, exponential increase. Very simple. The ideal LED. Another intensity, or maybe look some intensity, okay, or some maybe call as some electroluminescence intensity or something. This is a J. This is maybe another thing, the power or something. It's a linear. Okay. If it's a very large current, electron hole pair is a more electron hole pair generally is recombined, they generate line. It's a linearly proportion. Okay. This is a basic. Okay, this is a basic. Maybe master student can understand this. Okay, I just think it's not good enough for PhD student. Even now, it's not good enough. Okay. Here is very we call the Shockley diode equation. It's very basic. This exponential increase for this dark current, right? If we go to 0, we cancel them each other. Okay, because it's at thermal equilibrium is no current. When you add a bias, the exponential increase. Boltzmann statistics. They call it Shockley diode equation. And this current or depend on the intensity, just the intensity or emission light. It's just linearly proportional. It's good LED. Your LED is bad, it does not satisfy this. You will find something, or they are saturated, this is good. But something you have a no exponential increase, there's also no linear, there's some problem. You can check LED light. Okay. And for RPG students, what's the physical meaning of J0? What's the physical meaning of J0? This is important. What's the physical meaning of J0? J0 we call it dark current. Okay. Or reverse saturation current. Okay. So then, I think a dark current is better. What's the meaning of a dark current? They said the current is still here in vacuum, in a vacuum sealed structure without any photon. Okay. Without any photon. This dark current. Okay. There may be another dark current from some circuit, but that's not a key point because only this dark current can be exponential increase. Okay, can be exponential increase. So this is called dark current. Okay, how to express this dark current? Okay, the dark current J0. Everyone knows J is dark current density, current density. Okay, so see what happened. So we call this current density. It's just maybe I use J0. Okay, it's just delta Q over delta T delta S, right? And it's a change of charge with time is current, and over S is just current density. Okay, so I think important thing is if you learn physics, you should derive this by yourself. It's very basic equation. Okay. How about Q? Oh, I use generation rate. A Q, a delta Q over delta T. Okay, just N. I use N. Delta N or E. Okay, I use Q better. Okay. Delta S or delta T. Okay, just a change of the electron density or volume. Okay, this electron density. This volume is charge. Okay, charge density for Q. Okay, no problem. So I just change delta V over delta S. Okay, Q delta N delta T. Okay, delta V over delta S is L. Okay, Q delta N over delta T just generation rate. Q G L. So this is the same. G is the generation rate. L is device length. Okay. Device length. G is generation rate. Means how many electron hole pair or how many electron hole pair can be generated, okay, per unit time. Okay, how many electron hole pair can be generated per unit time. Okay, this is just delta M delta T. This J. This M. Very simple to derive this equation. Okay, so see G is how many electron hole pair can be generated at a dark current. Okay, how many electron pairs generated in the dark environment, in a vacuum? Okay, so what happened? G should be gamma spontaneous emission. It's very important. It's a PhD student, you should understand this level. Okay, that means it has balance. Balance. That means emission. It should be balanced with the absorption. The absorption just generation electron hole pair. Okay. Just one photon generation, one electron hole pair. So what's the situation? But how many electron hole pair generation just equal to how many photon they are emit? Okay, the detailed balance at a thermal equilibrium. That means they receive the vacuum in vacuum. The electromagnetic will fluctuate, and there's a fluctuation field. This fluctuation field will generate electron hole pair. Okay, the electron hole pair all recombine emit light. Okay, so this is spontaneous emission. We did not consider any non-relative decay. Okay, we didn't consider. So this should be balanced. It should be balanced. Okay, so generation rate just a spontaneous emission rate. Okay, how to enhance spontaneous emission rate? Okay, just increase, mathematically just imagine part green function. Okay, imagine part green function at this meter, or just field enhancement. Field enhancement at emitter point. Or just in LED, just enhance the field at active layer region. If you enhance the field at active layer region, I mean, this field is eigenmode, you know, it's eigenmode intensity. Eigenmode intensity. You increase this, you can increase the spontaneous emission, just increase the generation rate, just increase J0, just increase current. Okay. So the only thing you can change is J0. V is applied voltage. Maybe you can add too much, add too high because it will break down. Okay. So but you can change the J0. Okay. J0 just change the spontaneous emission rate. Just increase, just in for LED is active layer region. Okay, maybe this is electron transport layer, this whole transport layer, this panel is experiment. Okay. It just increase, just excite some eigenmode. Just excite some eigenmode. The eigenmode has two conditions. One, it has a resonance frequency around the transition around the emission frequency of the LED. Okay. This is one condition. Second condition, just in this eigenmode confined or had a field enhancement. It had a field enhancement and actively. Okay, so it doesn't excite some eigenmode. It has overlap. It has overlap with emission band gap, emission gap band gap. Another eigenmode should be enhance the field at its active region. So it can enhance the spontaneous emission. Enhance the spontaneous emission just enhance the generation rate, enhance the current, finally enhance the intensity, emission power. Okay, this is all the story. Okay, I think for RPTs you should understand this level. This level is enough. Okay, we'll go over how to do it. Okay. So in the last lecture, I talked about this Yaban knowledge, finite design. Okay, they said, if I put a dipole in here, put an active material, this is active material, they has a light emitting material. Okay, when they emitting light, the light will change and it's left with guided mode. Okay. So they use photonic crystal. Okay, use photonic crystal at a transverse direction and band gap. Okay, they cannot be guided mode at a band gap. So the light only can be emitted vertically. Okay, this is the idea. Then experimentally demonstrate. Okay, this is work. Indeed work. Okay, they use this experimental diagram. It has no photonic crystal, and the emission power is weak. This photonic crystal emission power is strong. This is experimental derivation. Another interesting thing, very recently work by Yaban knowledge. Everyone remember Yaban knowledge that it was 3D photonic crystal used, right? They also do something conformal square for solar cell, very famous guy. Also well invented photonic crystal. Okay, this side is spontaneous emission. This is published in Peanuts, quite recent. Okay, everyone knows Peanuts. It's a very good journal. Yeah, it's similar as good as the natural communication. It's the same level. It's a bilateral. This is only if you're academic for USA, if you're an academic member of USA, you can publish in Peanuts. Peanuts is difficult to publish. Okay. He do some spontaneous emission design. He wants to do that, but I don't think they achieve this target. See, they want to make spontaneous emission faster than stimulated emission. Okay, this is Yaban knowledge idea. They make spontaneous emission faster than stimulated emission. Okay, this is very magic. Everyone knows that spontaneous emission is very slow. It means, in unit time, they only emit a few photons. But stimulated emission in unit time emits many photons. So his target is make spontaneous emission faster than stimulated emission. So it seems very magic. Very magic. Now they are experimentally cannot achieve. It just enhanced 35 times. Okay. The paper claims that if we enhance 100 times, it can be achieved spontaneous emission faster than stimulated emission. Okay. This is the idea. And experimentally here is good nano antenna. Okay. They insert some active material, gallium arsenide something here. They put a TiO2 in here to make this contact better. Okay, this is the experiment. Okay. First thing that because it's a plasmonic enhancement, so the gap, the field at the gap is very, very strong. Okay, due to plasmonic interaction. So if you add enhancement here, okay, enhance here, so they can enhance the spontaneous emission. Okay, enhance spontaneous emission. This experimental study is very interesting. First, they add some weak source, maybe something is white polarized. Okay, you can see this blue line and the green line is almost same. So blue line is just bare, nano rod. Green line just add some antenna. Okay, sorry, add some it's bare Yeah, it's antenna coupled. Okay, so it's almost that. It's Y polarized. But it's X polarized. It's quite different. Because X polarized, it's okay. So it is a very strong E field. It can enhance. Okay, it's a spontaneous emission. We enhance this quite strongly. Helium we can enhance 35 times. Okay, so this is a very interesting experimental demonstration. You can see this is very interesting work. Just study the spontaneous emission issue. It's a very standard structure. You use a nano antenna plus modifier can enhance the absorption. Here, just enhance the emission. Okay. Because absorption and emission are balanced. It's by our knowledge. A very rich name. Okay, so I finished the LED part. I just call out nano fabrication. I hope everyone can understand the detailed balance. Okay, the emission and absorption, they are balanced at a thermal equilibrium. And non-thermal equilibrium just exponential increase by the Boltzmann statistics. This physics is such a universal in all the semiconductor devices. Okay, thermal equilibrium balance, generation recombination balance, some kind of balance, emission and balance. Okay, and non-equilibrium is exponential increase. Okay, other practical issue, other practical issue. Just change what? Just change this. The V here maybe minus R equal to J is some series resistance, a shunt resistance. It's due to some transporting layer, like some barrier, or maybe some defect. Okay, this is just practical things. Okay, this is ideal thing. This is ideal thing. Okay. Everyone can think about this, how to enhance the spontaneous emission of the area. This is very important. I talk about this nano fabrication. Now I almost need not to write the equation. Okay, I call this a fabrication. It's a quite simple one. It's my appearance on this topic is very weak because I did not fabricate any patterns or materials. So I just introduce this very big. So I just show this what I'm talking about. Okay, it's just talking about is global view of nano fabrication, their classification, or their resolution. And we talk about this two category method. We call top-down method, just and the bottom-up. I also talk about doping, etching, and decoration. Okay. So why do the meaning? It's a nano scale, or why make the device or structure very small? They give the reason. It can be faster. They can reduce the power. Okay, they can do the integration. They can increase the selectivity and sensitivity. It's a wide dynamic range of many advantages. So why I list this? I think very important. When you write a paper, you should give a very nice title. Okay, very nice title. Oh, this maybe a novel LED design with ultra fast response or something. Right, you should use with a very power, a low power or something. Right, you can use this word or some it's what's a photo detector with wide dynamic range. Okay, but just copy this name or low cost, high performance and ultra fast nano antenna or something. Okay, just this. Okay, this is the reason. Why write title is very important. Just you can see, let's see, copy this name. Okay, when you write your paper, you should use this technique, keyword to make your title is attractive. Why? Now we have many journals. When you publish paper, for example, publishing applied physics lecture, when it is not high enough, impact is not high enough, maybe people do not read your paper. Right? For me, I do email alert. Each month, I receive an email alert from APM. I just read the title. Oh, this title is attractive. I just read that. Read the abstract. I said, oh, this abstract is interesting. I just read the paper. If your title is not attractive, people just do not read your paper. They do not sign your paper. They just ignore your work. This is very important. So how to give a keyword such as this? Faster, or maybe sensitivity, or simultaneously achieve the selectivity and sensitivity. You can write a very nice title for this keyword. Okay. So this is the important thing. Okay. different field, maybe nanoelectronics, material photonics, mechanics, or many nanofluid also very popular. Okay, it's a different field. I like this word. Okay, but Feynman. Feynman is a great scientist. Okay, it's the most very famous Feynman because there's plenty of room at the bottom. This is his talk. When he talked in the APS Society meeting, okay, he said this sentence. After his talk, a nanoscience exponential impulse. It's very famous. He said there's a plenty of room at the bottom. That means at the molecule level, there's a lot of things can be done. Okay, this is his idea at that time. Okay. This is my Feynman. Okay. It's motivation. So since for nano fabrication, it has a 5 parts. Okay, you can see that. First, you can revise the property of material. Okay, just doping. Okay, just doping. You can use diffusion method or ion implantation method. Doping this material. When you doping the material, you can change the electrical property, optical property, mechanical property, thermal property. You can change everything. The doping is quite important. Okay, no doping, no p-n junction, right? Okay, so this is quite important. Another is the padding. Okay, just write some metamaterial or photonic physics to do the padding. Okay, and two category method, one is called top down, one is called bottom up. Okay, top down means okay, we have the bulk material and then cut them. Okay, just make them with a padding, just from a top, from a large scale to small scale. Okay, we call it top down, like lithography, optical lithography, E-beam lithography, ion beam lithography, many lithography. Just with the bulk material, just cut. Another is from bottom up method. We call it self-assembly. Just they use very small particle that assemble them to the large scale. They from small to large. Okay, they call it bottom up. That padding. Another is to look at some, subtractive process like etch, white etch and dry etch. Okay, they will etch something. They will want to remove something. They call subtractive process. Another additive process. Like oxidize something, like kind of evaporation or deposition. Okay, you can add something to the evaporation. This is very important because no university studies the packaging. Packaging is very important. If for LED or solar cell, I remember the World Trade the group they fabricated the solar cell, organic solar cell. If you do not do the packaging 3 days, right? Last time 3 days, so I was everything gone. Okay, so packaging is critically important. But university did not start this, just industry. But it's really important. Okay, packaging. So this picture is interesting. You can see here. Okay, this is skill. Okay, you can see the difference in DNA, protein, or cell in your mouse. Different skill. Okay. They have 2 methods. One is called bottom up. It's from small to large scale. Okay, from small colloidal particle. Okay, they assemble them to a big object. The bottom up. Another from top down, just cut a bulk material with some pattern. From large to small. Okay, you can see the complexity. Okay, for this bottom up, you can see this area. This is easy for small scale, right? Because it is from the colloidal particle. But if you make a small, very small nanoparticle, I mean, make out some molecule to a large scale, it's difficult. So it becomes multiple complex. This is from top-down method. Okay, it's easy to make a large bulk material, but very difficult to make it. Very small, very small pattern. Okay, so this is a contradiction to method. This is the top-down and bottom-up. This is something I think is important. Okay, you can see this resolution, different technical resolution. You can see this. First is optical lithography. Okay, this optical lithography range. Okay, they get down to around 100 nanometer. If you make a gap, I want to make a 10 nanometer gap because this gap is small, the enhancement is very small, the plasma bonding effect. I can make it break down. You cannot use an optical lithography. Okay, you can see E-beam. E-beam is better. Theoretically, they can do the 1 nanometer, but now only 10 nanometer. They can do a 10 nanometer E-beam lithography. Okay, X-ray become better, right? Because optical lithography use UV light. X-ray is a higher frequency, right? Higher resolution. Okay. Another is near field lithography. I believe they harvest out less away. Okay, they harvest out less away. Very neat. You can auto chip very easy. You can see their chemical method. This can be very small level, can be chemical method, to some molecular level. Okay, some chemical method. Very small. Another is deposition of epitaxial groups. This is a very interesting figure. Okay, this is for experimental figure. I copied this theoretical figure. Okay, it's very theoretical. It's another big field. Remember electromagnetics? I said, oh, if the wavelength is much longer than the object, it's electrostatic physics. Which compared to the object is wave physics. If the wavelength is very short, object is very large, it's ray physics. Right? It's ray, like lens, ray physics. Okay, if object is small, maybe we have a semi-classical and quantum electrodynamic approach. They call different scale with different method, electromagnetic. This is for electron. Okay, I teach this in auto electronics. I teach this part. Okay. You can see here they have very important three different scales. One we call this electron wavelength. Electron wavelength is very small. Why E-beam? Why E-beam can achieve a very 1 nanometer? Because electron wavelength. They use electron to strike, to collide or something. Okay. Electron wavelength is 1 A, 10 minus 10 meter. Okay, 0.1 nanometer. It's electron wavelength. And this regime is quantum, fully quantum regime. You have to solve the Schrodinger equation. No other choice. Schrodinger equation. Another, it's larger. We call it mean free path. What's the mean free path? For the one electron to collide something, maybe deflect or collide something other electrons, they change momentum. Like when they collide, you change momentum. The distance is just from one, from maybe they move, okay, strike something, okay, this is the distance. Okay, they call this a mean free path. Okay, that means the electron will move. Okay, strike some another electron. This distance, they call the mean free path. Mean free path. RE. Okay. This is just elastic. Very important. Elastic interaction. Elastic. Okay. It just change momentum. Like a sphere. This change momentum, but not change energy. This is a LE mean free path. This should be larger than electron wavelength. And this region, we call it ballistic. What's the meaning of ballistic? It's very important. Okay. It's ballistic. Ballistic means if this length is slightly smaller than mean free path, the electron from here to here, no scattering, no any scattering. Okay, called ballistic. Okay, go here, no any scattering. Called ballistic. Okay. Ballistic is very important. Then it will become larger. We call the phase coherence length. Okay, they just inelastic. Okay, electron-photon interaction. They change the phase or change the energy. Okay, this become longer. Okay, you can see. And this regime, the behavior of electron like a fluid. Okay, like a fluid. We could make it like a fluid. So what's the traditional regime here? L is much larger than this phase coherence length. It's diffusive. This is for old IC. Okay, you can see. If a device length is much larger than the phase coherent length, it means there's many collision to change the energy of electron. Okay, change the phase of electron. So coherence nature, so electron like a wave. The coherence nature of electron is lose its coherence nature. Okay, so everything becomes diffuse, like a drift diffusion equation. Everything becomes diffuse in electron because there are many collisions. You change the momentum, change the energy. Okay, so the electron is not coherence. Okay, then I reduce the length to this fluid regime. Okay, then reduce the ballistic regime from quantum regime. Every different regime use different equation. You can see diffuse regime use drift diffusion equation or Boltzmann equation. Okay, or this fluid use hydrodynamic equation. This is quantum mechanics equation. Different regime. So this is important But how about your size of your device? It's quite important. Okay. What's the physics here? Okay. I hope everyone can understand it's a coherence length, mean frame length, and electron length. Okay. Okay. Electron length just electron like a waves. It has coherence. Okay, the waves. Okay. Mean frame length it means it's a change of momentum. The length. Okay. Minimum length, the momentum change. Okay. Change the momentum. And the phase coherence length means the change the phase or change the energy. Okay. So LE phonon part it should be like the LEE part should be like the lambda part. So this is a different scale. Okay. You should very care about this scale. Okay. And the physics is quite different. They are behaving or diffusive. Okay. Everyone know, right? If something collision many times like diffusive because of no coherence. So you can see, our textbook in classical semiconductor textbook, they mainly focus on this regime, diffusive. Use drift diffusion equation to study this. It's old IC, current IC, the physics is at least following. Now Intel has changed the channel length to 7 nanometer. 7 nanometer, I believe, the ballistic, like this regime, very small. Everyone knows that smaller than 10 nanometer, quantum confinement, quantum effect, okay, become very significant. So this regime, this is knowledge, they have knowledge gap. Okay, it's all students have knowledge gap around knowledge around the fluid and ballistic quantum. This regime, that regime is very old, very old. So this is for the electron part. So this is another big field. Okay, maybe I'm sorry to teach you this. Okay. Now I talk about this lithography. Why is this? Okay, this is lithography. Lithography, I think is a very basic technique. It's a top-down, okay, from large scale to small scale. Okay, I talk about optical lithography first. Okay, optical lithography first. For optical lithography, okay, there's many different stages. Okay. But first, typically we have substrate with silicon. Okay, then we can deposit some thin film. Okay, this is a normal state. Okay, you can see here, this substrate. Then we can deposit or oxidize some oxidize the substrate from silicon outside. Okay, this first. This does not relate to the physical. It's very standard. Maybe we also can deposit other material above the substrate. Here, just oxidize the silicon outside. Okay, I think the third is spin photoresist. Okay. We spin coating the substrate with a photoresist. Okay, this is a photoresist spin coating. A spin coating is a solution, a photo solution, and then rotate that. The method is very uniform. Okay. The thickness, typically the thickness, over this resist, the thickness, it depends on speed, and viscosity. Speed. It become here. The photoresist with the spin coating. So there is a different photoresist. One called positive, one called negative. Okay. With the positive resistor, when use UV light to expose this area, it will dissolve in the development stage. Okay. If negative, just expose area to remain. Okay. I'll talk about this later. Okay. Then we do the soft bake. Okay, just heat up. Okay, with a low temperature from 60 to 100 degree. Okay. Because they want, when you do a spin coating for this photoresist, you must use solvent. Okay, you must use solvent. Very important because some material, this photoresist material is not soluble in water. You use other solvent to make them together and do spin coating. Okay, then you heat up called soft bake to remove the solvent. Remove the solvent. Remove that. Okay. But to improve the adhesion. Okay, just remove it. Okay, this is something like this. Just spin coating and then soft bake. Then we just expose with light. Okay, expose. Okay, this mask is very important. I mean, below the mask here, the light cannot be exposed at this region. Okay, at this region, the light can be exposed. So this is the main purpose of optical lithography because diffraction limit, or diffracting effect. Here, you know, it's not ideally. Okay, the boundary is not ideal because it has diffraction. Maybe here it also can be the tone here. Okay, not ideal. So this is the main purpose. This is okay. There's a photon mask. Okay, the exposed source. Okay, depending on the resolution, we can use a mercury lamp. Okay, this will achieve maybe 300 or 1400 nanometer resolution. Typically, we use deep UV source, UV light, because UV light, the wavelength is shorter. They can have higher resolution. You can achieve a higher resolution with UV source. We impose that. Okay, with UV source. 5 or 6 step. Okay, just impose a line and a line. Okay, impose a wafer. The 7th step, just we call developed. Okay, you can see that this is a we call this. Because they have different with a positive resistance. Because positive resistance, UV exposed area will dissolve in the subsequent area. You can see it's a UV exposed area here. It's UV exposed area. Okay, it is here. Okay, it's here and it develops there. It develops there because positive resistance. Okay, you can see they move by some another maybe chemical or something. Okay, they will develop. If they move by another some material can remove that. So after exposure, the photoresistance is developed. Okay, it's developed. Okay, then we do the hard bake. Okay, you can see temperature is different. Okay. Hard bake is higher. It's from 100 to 800 degree. Okay, to improve the adhesion, similar to consolidation. Okay. And make this mostly. Then, from until here, finish. Because we just finish the pattern. Okay, we finish the pattern. This pattern just follow this. Okay, I finish this pattern. I did finish. This is finish all the lithograph. This is each and is another step. This is a basic step of optical lithography. It's not difficult. Okay, not difficult. It just use mask to some pattern. Use mask to some pattern. And shine the light. Okay. And then I do the development to remove this exposed region. You can do a very complex mask. Okay. You can do very complex mask. That is, you can do some mask also like this. You can do some mask. Here, some mask also like this. And do some very complex mask. So after, let me finish. So after this development stage, okay, after development stage, the photoresist has a pattern. The photoresist has a pattern you want. Okay, you know the mask, photoresist. Okay, after development stage and a hard bake stage. Okay, so what's the next step? Next step we have a different choice. So when the common choice is to etch. Okay, you can see the etch the oxide. Okay. Etch the oxide. Why they can etch the oxide? Because there are some etch. The agent, some agent. I mean some agent can selectively. It means they only etch this oxide, but does not etch the mask. You must select the material very carefully. They only etch the oxide dye region, does not etch this mask. I talk about this later for how to etch. Etch them, you can see. They remove this part called etch. Then we can remove the photoresistance. Okay, in some organic solvent. Organic solvent. That's finished. We also have another choice. Okay, many choice. You can deposit metal. Okay, you can see here. You can deposit metal. The red color is metal. The blue one is a photoresist. It's photoresist. Then you can use the lift off technique to remove this part. Remove this part. Okay. Only the metal here just remain. Okay. It's another choice. can do the edge. You can see, okay, the edge is outside, silicon outside part. Okay. It also can do the grooves, also do the door. Okay, this is after the lithography. After lithography, you have many different choices. Okay, you have many different. You can door, you can edge, you can maybe lift off, and many choice. Okay. So the important thing that you must form a pattern over this photoresist. Okay, if we don't have the pattern, we can etch the other part, etch the outside part, or maybe definitely some metal. Okay, and remove the remaining part only has this metal. We also can groove some material. Okay. So this is a basic process. Okay. So this it's very important for optical lithography. But the main problem of optical lithography is diffraction limit. You should do very short optical wavelengths to make the resolution high enough. They cannot be cheap. Okay. So it's a low resolution. Okay. Low resolution. So the E-beam, okay, E-beam is very famous, but very expensive. In Hong Kong, we only have one. I remember only have one equipment, right? You must order that, pay money with that. Okay. Only have one in Hong Kong, very expensive. Okay. But it has an advantage, no diffraction limit, no mask, can produce small size, very small. Okay. This is advantage. You can see everything is very similar, but they use electron-sensitive resistor, not photon-sensitive, electron-sensitive resistor, PMMA. Okay, they call PMMA, very famous. They call PMMA. Okay, this is dissolved in some material, and depending on positive or negative, can dissolve. Okay. I cannot pronounce it. It's very complicated. So this electron beam just from the TEM or SEM. Okay, this electron beam and from TEM or SEM. Then you can collide this region, okay. We control the position. We control its position quite well. We move its position quite well. Okay. You can see here. This region, just electrons strike this region. Strike or collide this region. Then the development, we can remove it. With some solvent. With some solvent here, very long line, the positive solvent with the negative solvent. Okay. Then you can evaporate metal, lift off. Okay. So everything are very similar to optical photolithograph, but the difference thing is that we use electron. The electron here is electron. This electron, they can move. You use electron to strike it through the electron collide, not a photon. The electron can be very focused. So this is electron lithography. But the electron lithography is a problem. Even though electron wavelengths can be around 1 nanometer, but in real situation, because I have electron scattering, we only can achieve a 10 nanometer. But I think it's good enough. 10 nanometer is good enough. It's very good. Okay. But the problem is that here. Okay. Large area. Why? You do a very large area, maybe millimeter. Why? Very time consuming. You have to move. Okay. Very expensive. Okay. Or low throughput. Just cannot mass production. I want to do 100 samples. Give me 100 samples. Very time consuming. Each sample I remember need 10,000 or 20,000.
No, in US around 5 to 6,000 per 3 hours.
Oh, 5 to 6,000 per 3 hours. Okay. Very expensive.
Yeah.
But if you want to do the metamaterial, okay, if I want to do a metamaterial in plasmonic metamaterial, you should use this because I think it's good. You have no choice to do some demonstration. If you do the photonic crystal, maybe it has another different choice. It's an E-beam method. We have break fact. No equation. 终于没公式了。Okay, so not good. So wet etching similar to that. It's wet etching. It's typically isotropic. Another but they have very good selectivity. Okay, they can select the mask, and this oxide layer or something you want to etch, you can select this wet etch. Okay, typically you use acid. Okay, use acid, like silicon nitride. They can use some acid. Okay, and the silicon oxide and the mask use some acid, so they can wedge them. They have a different category. But this method, now, people do not like use this method because it has some problem. Okay, it has some problem. The viral problem is isotropic. You can see it's not good. It's wet edge. Another thing, but in a wet edge, typically also you should keep temperature, the high temperature. Okay, it's a wet edge. It also can wedge etch the metal. Okay, the metal just use some acid or some solution. Also can etch the metal with this method. And I want to talk about this dry etching. Dry etching now is very popular. Yeah. So typically it's plasma. It's a base. Okay, plasma base or ion meaning base. Okay, ion meaning base. There's no any solution. No any solution. Okay, they can etch something. But so the dry etch, problem is selectivity. Okay, selectivity is worse than wet etch. Wet etch has good selectivity but isotropic. Okay, this is anisotropic. They can achieve anisotropic, something like this. They can achieve with very good pen. But the selectivity is not good. This we call this dry etch. You can see that they have different picture. One is ion meaning. Okay, ion meaning is you can see this is the ion speed up, collide. Okay, the atom will remove out this ion meaning. Okay, this is ion meaning. But the plasma base, they call the plasma etching is quite different. You can see it's a little bit complicated. It's an interesting thing. You can see the plasma etching. When you do the plasma, look here, you can see they excite something called violet product. Okay, violet. Wallet. The means is easy to diffuse away. Very easy to diffuse. Very easy to evaporate. Okay, you can see here. When we use plasma to to excite it here, it become here. It will remove away. We call it volatile. It's similar to some material, it's easy to evaporate. But around here, it has non-volatile species. Okay, non-volatile. They will become okay. They do here the surface. Surface they become this. They call surface passivation. Okay, and surface passivation. You can see this picture. I mean, they call surface passivation. Because why they only accumulate here? Because around it cannot accumulate here because ions are here. The ion will remove this circle. This circle is just some non-volatile species. Okay, they make surface passivation. Okay, so it's isotropic. They only can etch here. Okay, it cannot etch here because it has some passivation. By a non-violet species. It's a non-violet species. This material, this species only can be removed by these ions. Okay, by these ions. But so you can see here, in the middle region, it has notice only has edge. Ion is difficult to arrive. Okay, so this they can passivate the surface, called surface passivation. Passivation is very important. If you want to remove some dangling bond, right? Silicon has some dangling bond, or some solar. It has a very strong surface recombination. I mean, electron and hole maybe they recombine here. Okay, they use the surface passivation. They passivate the surface. Okay. So plasma etching, interesting that they are automatically passivate this surface, vertical surface, and vertical surface. So they can achieve this anisotropic edge. Anisotropic edge. Okay. They can achieve it. This is what's called the dry etching. Tomorrow you use plasma etching for your graphene. Also graphene. Okay. I hope you can know how to realize. I don't know how to realize, but the principle is quite different. You can see that. This only has ion atom okay. They have many different species. We call them volatile, non-volatile species. The non-volatile species is the passively the surface. Okay, the magazine. This is very interesting. Okay, it's what graphene establishes. And it's for edge. As deposition. Okay, deposition is another way. Okay. We call it a chemical vapor deposition, CVD. Okay, CVD is very popular. We call CVD, chemical vapor deposition. CVD just the reaction chemical in gas phase, everything gas, then form a deposited CVD. Okay, they put some material, material in the gas phase, and then it can be deposited on this surface. Okay. Another just they can use plasma optic excitation, okay? Because the antigen need to chemical reaction just maintained by the substrate at a high temperature. Okay. First thing you must use gas. Okay, the gas is some material there. Go here. Must heat up. Okay, very high temperature. Okay. Now they can do a chemical reaction. This is important. Very important. Do a chemical reaction. If you use plasma or optical excitation, the temperature can be reduced. You can use a low temperature. Okay. This is a way why people use some plasma to reduce the temperature. This is several different types CVD. I just talk about this plasma enhanced CVD. Okay. For the plasma enhanced CVD, okay, plasma enhanced CVD they use RF annealing to create a highly reactive species. Okay, it has an RF source here. This RF source here is a gas. Okay, in plasma. They use plasma. The plasma can be by the RF source. So they can use a lower temperature. You can see. Low temperature is not so low, you can see. 150 to 350 for low temperature. Because they use RF source to create a reactive species in the plasma with RF source. From gas, then they deposited the wafer. Okay, deposited the wafer here. Okay, this is heat up. Also can be heat up. This is also another equipment. Okay, there's a vacuum chamber. Okay, this RF source, the gas from here, and then they have some plasma interaction and deposited around it. Okay. This is also has a temperature. You can see it has some temperature. Controller to control the temperature. That is plasma generation. This plasma generation just make this substrate temperature is not too high, so lower. With RF to create a reactive species. Another CED called epitaxial growth. Okay, epitaxial growth. I don't think so. I don't think that our department some staff can do this. But it's very, very important because a single crystalline material grows and expansion of the substrate. Okay, just maybe I remember now. Computer use silicon, right? Use silicon material. So people want to change to the 305. You must grow a 305 on the different substrate. Okay, that's very important because they have an issue. It's possible to grow a dissimilar material with a crystal structure similar. We call it lattice match. That is some material. If a silicon substrate you want to become gallium arsenide, it's quite difficult because maybe they are not match. Their lattice structure not match. Okay, so this is quite difficult. Okay, see, but it's possible to do that. So China invest a lot of money do this kind of thing. Just maybe we call it A63, very big project to support this. Just abstract groups, material in different substrate. So this groups is can use several chemical vapor deposition. Similar to that, it's a gas. Okay, it's a heat up. They're very similar. This is a heat controller. Okay, and they can depth it here. Okay. This is gas. You can see different gas from here. And inject different gas. Okay, from here and go here. You can see how much gas they use. Okay. If I want to deposit gallium arsenide, we use gallium arsenide CH3, this material, with gas phase, and arsenide H3. You can see, they use this material because they can remove this part, become gallium arsenide. Okay, this material, GaCH3, this gas phase, and arsenide as gas phase. Okay, they pull all the gas from here, and go to this region, they heat up. And they can deposit here. This is another called molecule. It's called metal organic chemical vapor deposition. Very similar. You can see it's H2 carrier, arsenide H3. Okay, gallium arsenide CH3. They put them three together. It's called dolphin. Okay, dolphin dog. Pull them. Everything, all the things are gas phase. All the things put gas phase. From here. Then inject, okay, they have some to the substrate, okay, and they can heat up them. They can heat up the substrate, make the chemical reaction. They have thermal couple. They just control its temperature. Okay, just control the temperature. So this method, I think, is very elegant because it put every element on. Every material a gas phase, GaCH3, IS3, carrier, dolphin, every gas. Just heat up and make this depth. Very simple. You can control the thickness. So the CVD. So CVD is very important technique. If you are a chemical researcher, okay, if you want to focus on chemical composition material, I think this technique you should know how to use this technique. Okay, it's very important. We can maybe graphene. CAD. Many can do CAD, right? You can do CAD. Another called physical vapor deposition. Physical vapor deposition. Okay. Physical vapor deposition is different because source, the material to be deposited, okay, is transported from source to wafer, and the source and the wafer are all same chamber. It's a chamber, all same chamber. Here, what about source? Source is from here, they will inject here, they become gas. Okay, not same chamber. But the physical vapor deposition, all are everything are same chamber. Same chamber. Okay, you can see, they use E-beam. They have some magnetic field. They can deflect the E-beam. Okay, and then inject here. The E-beam they can incite, they has collide. They will incite some evaporable material. This evaporable material evaporates, then evaporates wafer. Evaporate out this wafer. Because this is source, evaporable material. Okay, they put this source in. They call it I don't know how to read that. Crucible. I don't know how to read that. It's very complicated. Okay.
Crucible.
A crucible, okay, this crucible. They call it crucible here. Okay. You can see this is source. The source is decided by the E-beam, by the E-beam and evaporates the density. Everything at the same chamber. They also can use ion beam, use sputtering with ion. Ion at very high speed. Okay. They inject some gas very high speed. Okay. This is ion to strike this atom. Then they can incite some sputter target atom, okay, from this sparking target. And this sparking target atom is deposited in CPU. Okay, everything are in the same chamber. Everything are in the same chamber. Okay, called physical vapor deposition. Okay, this is I don't know which university can do this. I don't know they can do this. It's very complicated.
NIL.
What was it?
NRL.
They can do this? Okay.
E-beam sputter.
Okay, sputter. Okay. E-beam, they have to put them together.
Different chamber.
Different chamber. Okay, different chamber. So this is a sputter, and you have to do this sputtering with this. This is the last page. Maybe we can finish this. We can. Okay. Because I cannot understand it deeply, because I have no planning here. I just give a basic, very basic introduction. But this is I like this method because self-assembly is bottom up. Just aggregation some colloidal nanoparticle to the desired structure. Okay. Okay. Why they can aggregate? This is important. Why this nanoparticle can aggregate? Okay. They have two reasons. One called spontaneous, due to thermodynamic law. Everyone knows that for any system, there will, the molecule or some particle will move, okay, to a final stage, make this total energy, minimize the total energy, make it stable, okay, make it stable. Then you heat up the sample, heat up this nanoparticle, and cool it down, then move around, just make it very stable. This is called thermodynamic minimum, the energy minimization. This is one method. Another just due to the chemical reason, okay, just binding some organic material or super molecule, called molecule self-assembly. You can see from the first method, called spontaneous self-assembly, okay, the spontaneous self-assembly, okay. Spontaneous self-assembly, they just use a thermal assembly, maybe there's some another choice, gravity force, convective force, or electrohydrodynamic force. There are many forces. We can make some. Okay. So this pattern is very successful pattern. Okay. You can see here, this is a silicon oxide. It's a silicon oxide sphere. The sphere is a silicon oxide. Okay. The assembly on the silicon wafer. The silicon wafer is okay. The assembly here. Because there is a gradient over this temperature. If they use temperature, a temperature gradient across this sample. Okay, they make this assembly. Okay, they heat up this and make this assembly. They use some thermodynamic law to make this minimum. It's a very successful one. Very nice. Okay. I don't know how to do that, but I think thermodynamic law is key. Okay, they minimize energy. Also use another force. Maybe some fluid force. Maybe some vertical thing. They can also assembly something. But I think the most important thing is here, because this has been commercialized. I believe the because chemical self-assembly, okay, is commercialized. Chemical self-assembly, first thing, you attach a single molecule organic layer, we call it SAM. Okay, this is a good electrode. I put this called STREPTME. I don't know what's the name. This is just SAM. First thing, I just attach a single molecule organic layer. Okay. Then subsequently, we can self-assembling other material top down. You can see here. First, I use SAM over here. Then, I put the antibody. The antibody can be touched to this SAM called a single molecule layer. Okay. This is a pattern. Okay. This is an antibody touched to this single molecule layer. Okay. If we have an antigen, the antigen just reacts with antibody, also touch here. Okay, they can do this self-assembly from top to down. Why is it important? They can do the biological detection. Okay, first I put antibody. The antibody can only identify some maybe cancer or some disease. Okay, then I use your blood, just one blood. I put here. Because the blood has some this antigen here. The reaction happens. Maybe I use plasmonic technique. If reaction happens, they check the electromagnetic environment, the reflection, deep to the shift. You have this cancer cell. You have this cancer cell. Okay, you have this cancer cell. So they can do everything on chip. It's very small. Just use one blood, you can detect your disease. Okay, why they can just use the technique? Use a single molecule layer they call SAM layer, then do an antibody, touch them, and send to you. Maybe it has antigen. Okay, the reaction happens. Okay. Then they can do many different antibody, many different SAM in different cell, in different location, so you can detect them. So this is very magic. This is commercial one. And with antibody, antigen, they react them together. They can synthesize. Use a chemical cell for assembly method. Okay. So this is a very start of art technique to synthesize the nanofabrication. So let me show what I like to show this So I share introduction reading material to you. I think you can read all this and you can have a basic knowledge. We call it Introduction to Nanofabrication. Okay, this is a good material. I don't know why this is not shoot. Okay, this is very good. Introduction to Micro and Nanofabrication. Okay, you can read this. I copied a lot of figures to this. Okay, I also comment on figures to other sources to collect all the material together. My understanding in this field is very weak because I have no experience of fabrication something. So I can also make very deep talk. Okay. But you can read this, know the global picture of what kind of a technique. Okay, know this. This is not difficult, but it's knowledge. It's very knowledgeable, and you can read this lecture. Okay, so we can finish. Okay, thanks for attending. Is it easy?